We have been looking at one mean and two mean hypothesis testing. We finished up two mean t-test when you have independent samples, and we had started an example of the dependent, but I noticed there was some kind of weird thing going on there, so I want to backtrack to that. But we've been primarily focused on parametric test, which are the one mean z, one mean t, both of the two mean for independent as well as dependent samples, which we're going to look at, revisit today. But remember, when you're dealing with a parametric test, we are making the assumption that we have a normal distribution. So if we don't know or are not told that our distribution is normal, we may need to check that using the test for normality. And if our distribution happens to not be normal, then we may need to consider using a non-parametric test that typically will look at the comparison of the medians instead of the means. And so that's partly what we're going to look at today. I want us to kind of look at the parametric test and then look at its comparable test, which is a non-parametric test. So we're going to kind of combine together the discussion of a two mean t-test for an independent sample, and then look at Mann-Whitney U, which is the comparable non-parametric test. Then look at the two mean t-test for paired t-test for dependent samples. And then look at the non-parametric, which is comparable, which is called the Wilcoxon signed rank test. Okay, so we're still in that same section, and hope that we're able to get through that. So I did post, and I'll point it out to you in the course under Module 3. Oh, I'm forgetting to share my screen. Sorry. Let me get there. Okay, under Module 3, we're still under the topic one mean and two mean test, Mann-Whitney, Wilcoxon, and Cohen's D. And it's been taking a long time to load lately. But I went back to, I want to start with an example of a two mean independent sample t-test, which we did last week, but I want to let you see the difference or the connection to the non-parametric test. I did post, now that it's come up, a PowerPoint for Mann-Whitney. There's a data set from Minitab that we need. I posted it. I posted the PowerPoint for the Wilcoxon signed rank and the data set we need for that. And then in Word format, I posted the examples that we'll be using for Mann-Whitney and Wilcoxon signed. Okay. So all of that is available in D2L. And I want to begin with an example of a 2T independent test. Okay, again, this is one that we covered last week, but again, I want to try to help you see the connection to Mann-Whitney. So remember, when we looked at the independent sample T, that we recognize that we're doing that because it's going to compare two population means. We pull the same information from two different samples. Okay, and for our purposes, we do not pull the variances. And so I pulled a question. I didn't put this one on the, I just typed it in about 5 minutes before we started. So this is just so you'll have it, a two mean independent t-test. And again, I'll walk you through how we know that in just a minute, because again, that's one of the things you're going to have to be able to do, especially on your final, is to recognize which test you need to conduct. So this question says the local branch of Internal Revenue Service spent an average of 21 minutes helping each of 10 people to prepare their tax returns. The standard deviation was 5.6 minutes. A volunteer tax preparer spent an average of 27 minutes helping 14 people prepare their taxes. The standard deviation, it was 4.3 minutes. At a level of significance of 0.05, is there a difference in the average time spent between the two services? Okay, so one thing that I noticed, again, to try to help me recognize, other than the fact that Miss Ralston told you that, if you'll notice in this description, we are collecting information about the time spent preparing a tax return, which is in a sense our variable. That's the information we're collecting, and we are collecting that information from a local IRS office and from a volunteer tax preparer. So I'm collecting the same information from two different groups. Okay, so that is my clue, or kind of what I need to recognize to indicate that this is a two-mean independent t-test. Two, because I've got two different populations, okay, and we're only learning about the t-test. We don't do a z-test. So our first step in any hypothesis test, of course, is to state the hypotheses. And so we have the null, which always in some form contains equal, and we have the alternative, which in some form will not contain equal. Okay, so my last sentence says, is there a difference in the average time spent by the two services? So if I focus on that word difference, I hope that would make you think of not equal, because they're not the same, which means this statement is the alternative. So the mean for the IRS does not equal the mean for the volunteer. And that's the one that's given. So by default, then, the null is that the mean of the IRS equals the mean of the volunteer. Now you could label them group 1, group 2. Okay, I'm using IRS and V. Minitab does identify them as 1s and 2s. So I might say that the IRS is group 1 and the volunteer is group 2. In most cases, it doesn't matter which one is 1 and which one is 2, as long as you're consistent. It does matter with the p-test, with the paired test though. Okay, so step 2 is where we identify our information. In this particular scenario, we are given the summarized data, because in the first couple of sentences, it gives us information about the IRS. And then in the next couple of sentences, it gives us information about the volunteer tax preparer. And in each case, it tells us the sample size, the sample mean, and the sample standard deviation. So if I go back and read, it says the local branch of the IRS spent an average of 21 minutes helping 10 people prepare their taxes, and the standard deviation was 5.6. So we had 10 people, average of 21 minutes, and standard deviation was 5.6. Continuing to read, it says a volunteer tax preparer spent an average of 27 minutes helping 14 people, and the standard deviation was 4.3. So for the volunteer, we had 14 people, 27 minutes, and 4.3 was our standard deviation. Now, I do notice, in this case, this particular problem doesn't specifically say that the distributions are normal. So I'm going to add that. The distributions are approximately, because your problem really should tell you that. Again, because that's how you know that you're going to do the parametric test, which is the two-mean independent t-test. Otherwise, we would need to look at the distribution, but we have no way of doing that. So that really should have been included, and I do apologize for that. I typed it in a hurry. Okay, so then step 3 in the hypothesis test is to calculate the test statistic, which is going to be a t, and its p-value. And remember, we do that in Minitab. So I'm going over to Minitab, which I have not pulled up yet this morning. Okay, so Minitab is up. Remember, we go to Stat, Basic Statistics, a 2-sample T. We have the summarized data for sample 1, which was the IRS. There were 10 people. For my sample mean for the IRS was 21. My standard deviation was 5.6. For sample 2, which was the volunteer, we had 14 people. Mean was 27 with a standard deviation of 4.3. So I enter the information that I pulled out of the problem. It is a 99% confidence level, because I believe it said use alpha equals 0.01, did it not? Make sure I read it correctly.
I've got 0.05.
0.05. Okay, I'm sorry. Thank you. Okay, so it's 0.05. Let me change that. Our hypothesized difference is 0, because we're saying they're not the same, or they're either equal or not equal. We are assuming equal variances. I click OK. OK. Okay, again, remember, this tells us, it gives us, summarizes the information for us, gives us the sample size, the mean, and the standard deviation, which is the information I entered. It gives us the estimation for difference, which will allow us to calculate Cohen's d. But what we really need is our t and our p value. So I'm going to copy those over. Okay, so our t value, based on the data that we have, the t value is negative 2.97. The corresponding p value is 0.007. Step 4 then is to make our decision by comparing the p-value to the level of significance. Okay, so I would have my p-value, which came or comes from Minitab, is 0.007. My level of significance is 0.05. Remember, we compare that digit for digit. So 0 to 0, 0 to 5. 0 is less than 5, so P is less than or equal to the level of significance. When P is less than or equal to the level of significance, we reject the null. Now, step 5 then is to write our conclusion. Okay, so if I go back up here and I think through what this means, okay, we concluded that we're going to reject the null, which means the null is false or invalid. Therefore, the alternative is valid or true. So in this case, what we have proved or verified is that there is a difference in the average time. Okay, so we would write, remember, your conclusion must include your level of significance. So we would say at the 0.05 level of significance, there is a difference in the average time spent preparing a tax return. There's it between the IRS office and a volunteer tax preparer. Okay, so at the 0.05 level of significance, there is a difference in the average time spent preparing a tax return. Now remember, whenever we conduct a two-mean independent t-test, we really have to go one step further and conduct the post-hoc test, which is Cohen's d, to determine the effect size. Okay, so remember, Cohen's d is the difference divided by the pooled standard deviation. And we get that information from Minitab. It's already calculated for us. It's in the results under estimation for difference. So I'm going to pull that over here. Okay, so our calculations, our Cohen's d would equal -6 divided by 4.87. Get my calculator. -6 divided by 4.87 is -1.23. Then if you'll recall, we compare that value to the standard that Cohen established. Negative 1.23 is really below the large. Okay, so we would indicate that there is a large effect size. Okay, so there is a large effect size, and that's because negative 1.23 is below negative 0.8. And again, remember, we have to round down. Okay, now again, that's our two mean independent t-tests, which we had discussed last week. And again, we make the assumption with our independent test that we have a normal distribution, which allows us to compare the means. But probably more times than not, in the real world, we may have a distribution that is not normal. And so we have to have an alternative way to make a comparison. And that's the difference between a parametric test, which we just performed, and a non-parametric test. The comparable non-parametric test is called a Mann-Whitney U test, or it's sometimes called the Wilcoxon rank sum test. So I want to talk about it for just a minute. This will be new information, but it is the comparable non-parametric test. So Mann-Whitney U, which is sometimes called the Wilcoxon rank sum test, allows us to compare the medians, not the means, of two independent groups. So you're still collecting data about a single variable from two different groups. Again, it's comparable to that two mean independent t-test. Again, we're going to test whether two samples are likely to derive from the same population. That is, the two populations have the same shape. Okay, so the question that you're kind of asking is, do these two populations have the same shape with regard to their data? Are they either, both skewed left, or are they both skewed right, or are they both uniform? Do they have that common shape? Again, similar to the independent t-test, we have to indicate that we have simple random samples. Again, one variable from two distinct different populations. And again, if the sample sizes are small, it's important to know, and ideally, again, we want to have normal distributions, but if they're not normal, then again, we can use the Mann-Whitney U. That's really the whole point, is if we don't know, if we have a small sample and we don't know that they're normal, then we have to go to the non-parametric test. Okay? So some assumptions, and there's 4 assumptions that are made for Mann-Whitney U, the non-parametric test. First, you have that one dependent variable. You're collecting information on one thing, and that one thing is typically going to be measured either at the continuous level, so it's quantitative continuous, or it's at the ordinal level. So let me give you some examples there to kind of maybe help you make sense of that. For example, at the continuous level, we may be looking at something like time. We could be looking at IQ scores. We could be looking at exam scores measured on a scale from 0 to 100. We could be looking at weight. So those are things where you're measuring, it's quantitative, but it's at that continuous level. or your dependent variable could be ordinal. And more times than not, if we're doing Mann-Whitney, we're probably looking at ordinal data. So with ordinal data, think about sort of like what's called the Likert scale. You may not be familiar with the Likert scale. That's those surveys you get where it has, you know, strongly disagree, disagree, neutral, agree, strongly agree. So you have any kind of measurement scale like that. Even like a customer satisfaction, you know, like if you're talking about how much you liked a movie or something, and you could say, you know, hated it, and so good, or best movie I've ever seen. So anything where you have kind of that sense of ranking would be the ordinal level. So again, you're collecting information on a single variable from two independent groups, and typically you know, those two groups are dichotomous, meaning there's two outcomes. So something like gender, maybe your status of employment, you could look at employed or unemployed, looking at whether they're a smoker, that will be a yes or no. Things like transport, like transportation. You might have more than two for transportation because you could do bus, car, taxi, or so forth. But when you do that, if you have more than two, Mann-Whitney allows for that, but you can only compare two at a time. Maybe some kind of clinical trial where you have placebo and the actual drug. Okay, so typically you have a dichotomous variable. 3 is you should have an independence of observations, meaning that there's no overlap in the two groups. You have two distinct groups. What happens in one group doesn't affect the other group. And the last one is, again, our goal is to determine whether the distribution of scores for both groups, you must determine whether the distribution scores for both groups of your independent variable, oh mercy, I've left out a word, I think are the same. I think I left out a phrase, are the same. You must determine whether the distribution of scores for the groups of your independent variable are the same. I left out a phrase, I'm sorry. Okay. And this information, I've given you the link or the source for this information because it's not actually in the free OpenStax textbook that we use. So I've linked to the resource that was used to gather this information. And so we're going to take a look at an example of one of these Mann-Whitney U, where we might use Mann-Whitney U. Okay, so this example says a state highway department uses 2 brands of paint for painting stripes on roads. A highway official wants to know whether the durability, how long it lasts, of the 2 brands of paint are different at a 5% level of significance. For each paint, the highway official records the number of months the paint persists or lasts on the highway. The distribution for both brands of paint are not normal. Okay, and the data set that you need for doing this problem is in D2L. And we'll get to that in just a minute. I want to walk through the assumptions to kind of help you see what the assumptions are, and again, recognizing what this is. Okay, so assumption 1 is you have one dependent variable that is measured at the continuous or ordinal level. So in this problem, my dependent variable is the number of months that the paint persists. That's what I want to know about. Time is a continuous variable, so it's at the continuous level. 2, you have one independent variable that consists of 2 categorical independent groups. We have 2 different paints. They're calling them brand A and brand B. That's categories. You should have an independence of observations. Well, how long brand A lasts isn't going to affect how long brand B lasts. Okay, so there's no overlap, no commonality between the two brands. Okay, then you got to determine, here's the rest of the sentence. You must determine the distribution for both groups of your independent, whether they have the same shape or different shapes. And in this problem, they tell us that the distributions are not normal. But if they didn't, we could actually look at the histograms. And I'll show you that in just a minute. I have on the next slide the Minitab instructions that we're going to walk through in just a minute. So I'm going to go out. This problem is on the handout that I posted in D2L. Okay, so before I pull my data set up or into Minitab, remember that the first step in any hypothesis test, even if we're doing Mann-Whitney, and again, thinking about the biggest thing here that strikes me to let me know that I may be doing Mann-Whitney is that it tells me that it's not normal. And then I realize I'm comparing two things. I'm comparing brand A to brand B. The fact that it's not normal is the clue that I'm going to use the non-parametric test, which is the Mann-Whitney U. Okay, but my first step in the hypothesis test, even for the non-parametric test, is to state the hypotheses. It is still true that your null hypothesis will contain equal in sum format, and the alternative will not contain an equal. So we want to compare brand A to brand B. And let's see if it says, Fisher wants to know whether the durability of the two brands of paint are different. Again, I see that word different, which makes me think of not equal, which means that statement is the alternative. So I have brand A is not equal to brand B. They don't, or excuse me, I'm sorry, it's not the mean. Excuse me, sorry. Because we're doing Mann-Whitney, it's the median. Sorry. Okay, so we really are going to say the median for A does not equal the median for B. And again, I'm using median because it is not normal. Then my null by default is that the median of A equals the median of B. All right. Then step 2 is we identify the players. And basically, we're going to have to pull in the raw data. Okay, so in this case, you have the raw data, which is the Minitab worksheet, and we're going to pull it into Minitab in just a minute. We also know that our alpha is 5% or 0.05. Okay, so then step 3 is we calculate the test statistic. And this is going to look weird when I write it, but the test statistic is a W. And you may say, well, Mr. Austin, where do you get Mann-Whitney U? Quite honestly, I don't know. I tried to research it, but remember, it's also called Wilcoxon rank sum test. So I believe the W comes from the fact that it could also be called Wilcoxon. I tried to research it, but I didn't find any information other than the two tests are the same test. All right, so I'm going out to Minitab. And again, I have the spreadsheet in D2L4U. I have it on my desktop. So I'm going to open a worksheet from a local file. And this is highway paint. Okay, so what we get in our data set is you have brand A paint and brand B paint, and the highway patrol, the highway traffic engineer guy has recorded the number of months that the paint stays on the highway. Okay, now notice one of them we have a sample of 11, the other we have a sample of 10. It's okay, they don't have to be equal. All right, so we have our data. So here we go. We go to stat. We're using a non-parametric test. So I'm going to scroll down to the very bottom, kind of towards the bottom of the list, to non-parametrics. And we are doing Mann-Whitney. My first sample is brand A. My second sample is brand B. We're doing 5% significance level, which would be a 95% confidence. And we are looking at not equal. Now, again, from what I have been studying and researching in relationship to Mann-Whitney, you can also do, you know, a less than or greater than. But most of the examples and the problems that I've seen, again, as I was studying this particular topic, most times they're just simply looking for a difference, which is the not equal. But it could be the other. You just have to be careful about the wording. So I'm going to click OK. And again, it gives me the results. It gives me the method. It shows me the descriptive statistics. It shows me that I had a sample of 11, and it gives me the median. Notice this is the median, not the mean, and brand B. Then it gives me the estimation for difference, and then it gives me my test. Okay, let me copy this, and then I need to backtrack for a second because I didn't show you. Okay, it told us, remember, in the problem that our distributions were not normal. But if I did not know that, I could look at the histogram. So just to review, to create a histogram, we go to Graph, Histogram, and I can get it to show me both graphs at once. Okay, I've got multiple Y's. I want to do two different Y's separately. So I want it to do brand A, brand B, and I want it to create separate graphs. And I want it to fit a normal distribution. Okay, so let me see if I can get this up here where you guys can see it. Okay, so this is histogram A. I don't think you can see it very well. Let me pull it over here. Okay, this is histogram A. Now it does put in that normal distribution curve, but look at the graph itself. If you just look at the histogram, guys, that's not normal. I'm not sure what shape that is, but it's not normal. If I look at brand B, okay, again, brand B puts in that curve. It might be closer to being normal because I've got that normal curve in there. Maybe. But remember, they have to be the same shape. And they're not. Okay, they're not the same shape. And one of them may be normal, but the other one is not. So again, that would limit our ability to use the parametric test or the two mean independent t-test. Okay, so we've got our test statistic calculated. Now let me show you. We're going to use the one that is not adjusted for ties. Okay, because if you had numbers that were the same in both data sets, they would think that's a tie. Okay, so again, we're going to use the one that's not adjusted for ties. And so our test statistic, our W test statistic is 76.50. Our corresponding p-value is 0.002. And I need to look up the distribution for Mann-Whitney or the Wilcoxon. Again, we're assuming it's not normal, so it would not be the normal distribution or student's t. I'll have to look up. I forgot to do that. And it wasn't in the text that I was using. Okay, so then step 4, has it changed? Is we're still going to make a decision. Okay, again, by comparing the p-value to the level of significance, that process has not changed. So my p-value is 0.002 and my level of significance is 0.05. Again, if I make those comparisons digit for digit, 0 compared to 0, 0 compared to 5. 0 is less than 5, so P is less than or equal to the level of significance. When P is less than or equal to the level of significance, we reject the null. If we reject the null, that means the null is false or invalid, which means then by default, the alternative is true or valid. Okay. Now, there's a couple of ways you can write your conclusion. Again, you still include your level of significance. So we would say at the 0.05 level of significance, there is not a difference, or there is, excuse me, sorry, got an extra word in there because we're saying they're not equal. There is a difference in the durability of paint brand A and paint brand B. Okay. The question, remember, the question was, wanted to know whether the durability of paints are different. Well, we have proven that yes, it is different. Okay, we have proven that it is different. Now we could look, you're not really required to, but if we go back and look at our estimation for difference, notice that we get a negative value, okay, which means brand A is less durable than brand B. I believe that's what that means. I think that's right. This is a new topic for me, guys, and I'm struggling. I've been reading and studying and reading and studying, and none of it's really quite got my brain wrapped around it yet. But we did conclude, and that's really the conclusion that I want you to get to, is that there is a difference. We've determined that there is a difference. The process itself, in terms of hypothesis testing, has not changed. So I know it's been a little scattered, but do you have questions? Okay. So I want to go back to then the t-test, because we need to look at the two mean t-test where you have paired data. Okay, the two mean t-test where we have paired data. This is the parametric test. Okay, we didn't get to this one the other day, so again, this will be new information. So the difference with the dependent samples is you're using one population and one variable. You're collecting the same information from the same group of people at two different times. Remember, this was like pre-test, post-test, or before a new coach, after a new coach. Okay, so it's one variable from one group collected at two different times. And we assume that we are using simple random sampling, that every item had the same opportunity of being selected. We often use small sample sizes. Again, we have two measurements taken from the same group of people at different times. We then look at the differences between those matched or paired numbers. We compare pre-test, post-test, or before and after. Okay, those differences, okay, actually become your data. And we are looking at, we compare the mean of the difference. Okay, so either the matched pairs have differences that come from the either the matched pairs have differences that come from a population that is normal, or the differences are sufficiently large so the distribution of the mean is approximately normal. Again, because we're using the parametric test and looking at the mean, we have to assume that we have a distribution that is normal. That's the biggest key when you're thinking about a parametric test, is we're making the assumption that our distribution is normal. We either know for sure it is, or our sample is large enough that we can apply central limit theorem and force it to be normal. So again, I have the keystrokes for the two sample T dependent paired test in Minitab. Typically for this problem, you only get the raw data. Okay, you don't necessarily get a data set, get the data already summarized for you. So that's another difference. So I want to go out, and I have this on the worksheet from last week. And I think maybe we had started this problem, and I realized or have figured out what Miss Ralston's mistake was. This one says, A study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown in the table below. A lower score indicates less pain. The values are before and after hypnosis. The before value is matched to an after value, and the differences are calculated. And that's going to go on behind the scenes in Minitab. Those differences, okay, and that's important to note, the differences, because that's really what we're focused on, the differences have a normal distribution. Okay, and then the question says, are the sensory measurements on average lower after hypnosis? Okay, so I realized that before, the other day when we worked this problem, we looked at before minus after, but we're really interested in the measurements being lower after hypnotism. So we really should look at after minus before. Because of the way the question is worded, it matters which one is group 1 and which one is group 2. In this case, the after is going to be your group 1 and the before is going to be your group 2, because again, we're interested in it after hypnotism. Okay, so first step in any hypothesis test is to state the hypotheses. And again, we want it to be lower. Okay, so we're saying that the difference will be less than 0. So because it says lower, get all this going on here, you got to watch the words. Sometimes that's the hard part that gets us tripped up, is watching all those words. It says lower. So lower, at least in my mind, implies less. Okay, which makes this the alternative. So my alternative is going to be that the mean difference is less than 0, which means the mean difference is greater than or equal to 0 is the null. Again, the idea that the null contains equal and the alternative does not hasn't changed. Okay, then we have our raw data, which we will have to enter into Minitab. So step 2, we identify the players, but our players here are the raw data. And we do need to know alpha. Alpha is 0.05 because it says test at a 5%. So we then have to go out. Step 3 hadn't changed, is calculate the test statistic, which again in this problem is going to be a t, and its p-value. So I'm going out to Minitab and I'm going to get me a new worksheet so I have a clean sheet. And I have to enter the data, from that problem. Okay, it doesn't matter which one you put in column 1, which one you put in column 2, but you need to know which one is before, which one is after. So this is before hypnosis, and this is going to be after hypnosis. And we enter the data. from the problem, which I'm doing. So give me just a minute. And so put the before in, and then I'm going back and I'm putting the after. Okay, so we have the before and the after entered. Now, Minitab is going to calculate, because really what we need are the differences between those two. Okay, but Minitab is going to do that for us. So we go to Stat, Basic Statistics, Paired T. These are paired. Each sample is in a column. Again, because we're looking for it being lower after hypnosis, after becomes our sample 1, before is our sample 2. We look at our options. We're using a 95% confidence level. My hypothesized difference is 0, and we're saying that it is less than, because it's lower. Okay, again, if we needed it, Minitab has calculated the mean and the standard deviation for after, and the mean and the standard deviation for before, if I needed it. Okay, what I need is my test to get my test statistic and the corresponding p-value. Okay, so my t is negative 3.04 and the p is 0.009. Then step 4, we make a decision. I know y'all get tired of hearing me say that, because I have to keep saying it over and over. So we compare our p-value to our level of significance. Okay, so my p is 0.009. My level of significance is 0.05. If we make the comparison, we have 0 to 0, 0 to 5. 0 is less than 5. P is less than or equal to the level of significance. When P is less than or equal to the level of significance, we reject the null. In this context, if we reject the null, that means the null is false or invalid, which means the alternative is true or valid, which in this case means that the pain level was lower after hypnosis. Okay, it says, are the sensory measures on average lower after hypnosis? We've proven that yes, they're lower after hypnosis. Okay, so step 5, as always, you write the conclusion, including your level of significance. So we would say, at the 0.05 level of significance. The sensory measurements on average are lower after hypnosis, which seems to indicate that hypnosis is a plausible way for controlling pain, because that seems to say that hypnosis works if their pain level decreases after hypnosis. Questions? Guys, it's the same process of hypothesis testing over and over and over again. You are simply changing what test statistic you are calculating based on the information that you're given. Now, again, the piece in this problem that was important that helped us to know to do the paired t-test was that our differences have a normal distribution. Well, if we don't know that our differences have a normal distribution, then we aren't able to use the paired t-test. And we may have to consider a non-parametric test. The comparable non-parametric test is called the Wilcoxon signed rank test. Okay, now you got to be careful because it's the Mann-Whitney U could be called Wilcoxon rank sum, and this one is Wilcoxon signed rank. Okay, so you get them mixed up, so just be careful. That's probably why she chose to use the term Mann-Whitney U, to try to prevent some confusion. But the Wilcoxon signed rank test is comparable to the paired t-test. And again, we use it when our distributions are not normal, and instead of comparing the means, we compare the medians, and we look at the difference between the medians. And again, it's the same idea. You're collecting the same data, same information from one group at two different times. One piece of information from the same group at two different times. And again, we look at the differences. When using a Wilcoxon signed rank test, again, we want to assume or use simple random sampling, just like we did with the paired t-test. Again, we often have small samples, just like we did with the paired t-test. And again, we take two measurements from the same pair of individuals or objects, and we look at their differences. Okay, and the differences again from the sample are used for the hypothesis test. So we're using the differences, not the actual data values. We look at the difference between them. Okay, so I've given you the instructions for the Wilcoxon sign rank test. And then we're going to take a look at an example. And I do have these on the test or on the worksheet, and there is a data set that you need for this one. So let me get to Wilcox. Okay, it says a chemist for a pharmaceutical company wants to determine whether the median reaction time for a newly developed antacid is less than 12 minutes. The chemist measures the reaction time for 16 samples of the antacid and the chemist wants to know whether the median reaction time is less than 12 minutes. Use a level of significance of 0.05, and it tells you to see that particular data set. Now, it tells you in this problem to test the median, which means you're going to use the non-parametric test. But why did it do that? Or why would the chemist have decided to use the non-parametric? Because quite honestly, guys, if it's possible, we would like to use the parametric test. It's a more powerful test than a non-parametric. But sometimes that's not possible. So let me pull this data set in. I'm going to open the worksheet. I already have it on my desktop. Antacid reaction time. Now, in this particular data set, all they have given us is the difference. So I know that there was a difference of 10.9 seconds for the first one, a difference of 15 for the second one, a difference of 11.9. And guys, if we look at the histogram of those differences, you're going to see that it's not normal. Okay, this is the histogram of those differences. Again, it is by no means normal. I didn't draw the normal curve on it, but it's not normal. And so that would have been the reasoning the chemist used to determine whether the median reaction time is less than 12 minutes, because the distribution of the differences is not normal. So we begin the hypothesis test like we do any hypothesis test. We state the hypotheses. I got 6 minutes, so maybe I can do this in 6 minutes. Hypotheses. So we have our null and our alternative. Now, if I go back and read the problem, it says, determine whether the median reaction time is less than 12 minutes. So I see that word less than, which hopefully makes you think of the mathematical symbol less than, which means this is my alternative hypothesis. So I would have the median difference is less than 12. The median difference is greater than or equal to 12 would be the null hypothesis, because it has to contain equal. We already have our data set. I pulled it in so we could look at the histogram. But again, here what you have is the raw data. But remember that raw data is just the differences. And my alpha is 0.05. So then step 3, we're going to calculate the test statistic, which again in this case is W. Okay, they're doing the Wilcoxon signed or sign rank. Wilcoxon starts with W, so that's why you get a W. So here we go. We've got our raw data, which is the antacid reaction time. We're going to go stat non-parametrics. We're doing a 1 sample Wilcoxon. My variable is time. So 95% confidence. Okay. We want to test the median. In this case, that it is 12, not 0, 12, and it is less than. Okay. We're testing time. We wanted the median difference to be less than 12. So I have to enter 12, choose less than, click OK. Again, it calculates, if I needed it, the sample size and the median for the sample. And then it gives me my test statistic and the corresponding p-value, just like it always does under test. So my Wilcoxon statistic, okay, the W is 53. The P is 0.227. Step 4, as always, is to make a decision. Again, by comparing the p-value to the level of significance. Y'all should be experts at that by now. So you have 0.227 compared to 0.05. Make the comparison. 2 compared to 0. 2 is greater than 0. So P is greater than the level of significance, which means we fail to reject the null. If we fail to reject the null, that means that the null is true or valid, and my alternative would be false or invalid. So what we've proven is that the median reaction time is not less than 12 minutes like the chemist hoped. According to the data we have, it's actually equal or greater to 12. Okay, so again, we write our conclusion. And I know it's 12:15. So we would say at the 0.05 level of significance, the antacid reaction time is not less than 12 minutes. Okay, questions. I know it's 12:16 by my clock, so I'm a little bit over. I'm sorry, Jeannie, you're the only one left, but do you have questions?
No, I think I'm good. Thank you.
You're very welcome. I hope y'all have a good afternoon, and I'll see you Thursday.
Okay, take care.
You too. Bye-bye.